You wake up from a vivid, complex dream, and within seconds, your conscious mind dismisses the entire experience as random noise. The events seem too chaotic, the transitions too bizarre to hold any real logical structure. Consider this exact waking thought recorded by a subject after a highly distressing dream. Dreams follow random functions. No waking formula can present them in reality. The brain kinematics model, or BKM, proposes that dreams are strictly ordered nonlinear processes where the brain accumulates, transforms, and discharges cognitive strain. The waking mind's perception of randomness is a byproduct of its inability to consciously integrate a high-density, rapidly shifting flow of information. The structure is present. The waking mind simply lacks the resolution to map it. To identify that structure, we can map the chronological dataset of the subject's dream. The sequence proceeds from establishing a room with a mattress to the sudden emergence of insects, an urgent chase and kill, the discovery and killing of a second, beautiful insect, and finally, a feeling of regret. Because these events shift rapidly and carry mixed meanings, they resemble chaotic systems. The conscious mind analyzes this timeline and mislabels the complexity as randomness. We can decode the sequence by applying the Center Climax Mapping, or CCM, framework. This allows us to reveal the hidden spatial and temporal geometry dictating the dream's flow. By identifying these coordinates, we can translate the subjective narrative into the specific spatial and temporal data points used in the BKM. We begin by translating the narrative into the physics of BKM. The insects in this dataset represent fast-moving, hard-to-control neural disruptions. These disruptions act as strain packages, micro-scale conflicts that emerge from hidden subconscious cognitive layers. The dream setting, a mattress on the floor, represents the mind's memory substrate. This is the vulnerable foundation state where rest and identity stabilization occur. This graph maps temporal progression. The x-axis is time, the y-axis strain. We start at the memory substrate baseline. The line rises sharply as hidden strain packages, the insects, surface. The system identifies a localized internal disturbance rather than an external threat. The subject noted the presence of their children in the room. In cognitive terms, children act as a responsibility variable, amplifying the system's sensitivity to this rising strain. The highest level of cognitive pressure occurs when a foundational memory structure becomes unstable from the inside out. To measure this dream structure, we evaluate two independent variables, space and time. First, we locate the center of image, or CI. This is the spatial node where emotional and strain density is hyperconcentrated. In our graph, the CI occurs where the mattress and the insects overlap. This point functions as the local equilibrium attractor. Next, we map the climax point, or CP. This is the temporal moment of maximum strain amplitude, where action becomes unavoidable. For this dataset, the climax lands exactly at the moment the subject engages in chasing and killing the insects. The relationship between these variables yields the alignment index, measuring the overlap between the spatial center of image and temporal climax point. Here, peak action occurs in the exact same domain as the spatial focus, yielding an alignment index of 1. A high alignment index signifies a direct collapse into an attractor. This yields a type 1 dream, which is characterized by high coherence and a legible symbolic structure. In low alignment scenarios, the spatial and temporal peaks are separated. The system oscillates between attractors, resulting in disjointed, abstract dreams. Clarity within a dream always fluctuates according to the alignment between the spatial focus and the temporal peak. The dataset contains a turning point, the appearance and subsequent destruction of a beautiful insect. We can map the dreamer's decision-making process using an attractor landscape. It features two distinct nodes, a safety and elimination basin and an exploration and integration basin. Faced with the initial insect threat, the cognitive state variable collapses into a defensive posture. BKM defines beauty as a cognitive response to high coherence. When a strain package is highly organized and the motion is balanced, the system signals this structural order as an aesthetic quality. However, the system failed to adapt to this new variable. The responsibility of protecting the memory substrate kept it locked defensively. On the landscape, the new memory unit appears, but the system forcefully pulls it into the elimination basin, discharging strain prematurely. The system made a processing error, treating highly organized complexity with the same elimination strategy it used for chaotic complexity. The subject's regret is the result of delayed metacognition, the system finally detecting a lost opportunity to preserve meaning. The sleeping mind balances the requirement to eliminate strain for protection against the need to preserve structured strain for meaning. We return now to the subject's initial conclusion that the dream followed random functions and defied logical formulas. This 3D phase space diagram maps the alignment index, strain intensity, and coherence. The experience plots as a precise coordinate in region I, ranking high across all three metrics. This plotted coordinate is the measurable outcome of the spatial and temporal inputs. The perception of randomness arises when the waking mind attempts to track a system that failed to shift between its two primary attractors. The center of image dictates where the neural continuum concentrates. The climax dictates when it reaches maximum deviation. Their geometric alignment defines the dream's resulting meaning. Mathematical plotting shows the sleeping mind as an ordered system that resolves internal strain to maintain cognitive continuity.